Hello guys, today I'm going to discuss polymerase chain reaction. So, Sir Carey P. Mullis was awarded the Nobel Prize in Chemistry 1993 for the development of the revolutionary technique of PCR. So, PCR is an in vitro amplification technique that mimics the DNA replication, enabling the rapid and specific amplification of the target DNA sequences for the molecular analysis. So, DNA replication versus PCR. PCR is a laboratory version of the DNA replication. PCR occurs in vitro in a test tube. The DNA replication occurs in vivo inside the living cells. So, both processes involve copying DNA, but the environment differs. That is, PCR we do in the lab, DNA occurs inside the living cells. So in this slide, you can see how DNA replication occurs. This is the original DNA. This is the replication fork. This is the leading strand. This is the lagging strand, and helicase that unwind the two DNA strand into the single DNA strand. These are the free nucleotides, and this is the DNA polymerase. The components of the PCR, as you can see in this slide, is template DNA, DNA polymerase, primers, DNTPs, and buffers. And we take out the process of PCR in thermal cycle, or we can say thermocycle or PCR machines. So what is template DNA? The template DNA, the DNA which contains the genomic sequence to be amplified and may be single standard, double standard, though linear DNA amplifies more easily than the closed circular DNA. So even a single copy of DNA can serve as a template for PCR amplification. The optimal amount of template DNA depends on the sample complexity. So, too little DNA result in the low yield, while the excess DNA causes non-specific amplification. The high DNA purity is essential as contaminants such as phenol, EDTA enzymes inhibit Taq DNA polymerase. The purification using ethanol precipitation and 70% ethanol wash improves PCR efficiency. So what are the source of genomic DNA? That can be blood, tissue, culture cells, saliva, or microorganisms. And these are the examples. Blood can be human blood, animal blood, tissue can be plant or animal tissue, cultured cells can be bacteria or mammalian cells, and human oral cells, microorganism can be bacteria or fungi. And these are the required concentration of PCR per reaction. The second requirement for the PCR was polymerases. These are the quality of polymerases, that is specificity, sensitivity, fidelity, and processability. These are the quality of polymerases. So sensitivity, it refers to the ability of polymerase to amplify very small amount of DNA. The Taq polymerase can amplify low DNA concentration. However, it is less sensitive than some modern enzymes used for the rare targets. Second one characteristic is specificity. Specificity means how accurately the polymerase amplifies only target DNA sequence, because we need only the amplified copies of target DNA sequence. The Taq polymerase works well with the good primer design, and the poor conditions can lead to the non-specific amplification. The third characteristic of polymerases is fidelity. So fidelity is the accuracy of the DNA replication, meaning how often the correct nucleotide is added. The Taq polymerase has low fidelity. It does not have proofreading activity, so the error remains uncorrected. So there are about one error per 10 raised to power 4 to 10 raised to power 5 bases. The next one is processibility. Processibility refers to how many nucleotides the enzyme adds before it falls off the DNA template. Taq polymerase has moderate processibility, and it is suitable for the routine PCR, but not ideal for the very long and highly accurate amplification. So the third component we need for the polymerase chain reaction is PCR buffer. So the optimum pH for the PCR buffer is 8.3 to 8.8 at room temperature. So the buffer provides a stable chemical environment essential for the amplification. The tris HCl is a commonly used buffering agent to stabilize the pH during the PCR. And the potassium from the KCl enhances the primer annealing and can increase the DNA polymerase activity by the 50 to 60%. So divalent cations like magnesium, they are essential for the activity of thermostable DNA PCR in polymerase in the PCR. This magnesium, it binds to the primers and DNTPs and facilitate the DNA synthesis. So in addition to this, magnesium concentration must exceed the total phosphate groups contributed by the primers and DNTPs. And the optimum magnesium concentration is determined empirically for each reaction. So a concentration of 1.5 millimole magnesium is commonly used for the most PCR reaction, and the excess magnesium leads to non-specific amplification and reduced specificity. The next requirement for the PCR is deoxynucleotide triphosphate. They are the building blocks from which DNA synthesizes a new DNA strand. So the standard PCR contain the equimolar concentration of the following DNTPs, that is 200 to 250 micromillimole per liter. That is DCTPs, DGTP, DATP, DTTP. And these nucleotides, triphosphates, are supplied in the form of mixtures and available commercially. These nucleotides are available in the form of commercial mixtures. Next one is primers. The short segment of the nucleotide, that is 50 to 25 bases, are complementary to target the DNA template. The primer design is the most critical factor for the successful amplification of specific target DNA sequence. So the primer design depends upon the genomic sequence, nucleotide composition of the primer. And the poorly designed primer can lead to non-specific amplification, primer-dimer formation, reduced PCR efficiency. So the primer design is the most critical factor. These are the various steps of PCR. First one is denaturation, where we heat the reaction mixture to 94 to 96 degrees Celsius for the 30 seconds, and DNA melting by the disrupting the hydrogen bonds between the bases occur and that yield the single stranded DNA. The second step is annealing. Now the reaction temperature, we lower the reaction temperature to 50 to 65 degrees Celsius for 20 to 40 seconds. So we keep the temperature in the step low that the denatured primers can form the Watson-Crick base pairs with the template DNA. So this perfect annealing temperature is a few degree lower than the melting temperature of the primer pair. And during this step, the polymerase will bind to the primer template DNA complex. So polymerase will not start reading until the temperature is raised in the next step. Now, third step is extension. The Taq polymerase has optimal activity temperature of 75 to 80 degrees Celsius. So in this extension, we keep temperature around 75 to 80 degrees Celsius. And the DNA polymerase synthesize new DNA strand complementary to DNA template by adding DNTPs. And the extension time, it depends upon the DNA polymerase used as well as the length of the DNA fragments which has to be amplified. These are the steps of the PCR. First one is denaturation, annealing, extension, then the cycle repeats, and these are the various temperatures. This is the requirement for the PCR, that is DNA template, primers, DNA polymerase, DNTPs, buffers, bivalent cations. I have told about magnesium, then monovalent cation, that is potassium, we get from KCl's and additives. These are already